Hi class, this is section 4.3, which is logarithmic functions. Okay, so as you know, the idea behind this is so that I can go slower on examples in class, which allows me to finish the examples I was going to do on these videos. So I have 4 more examples that I want to do today, and the first one is number 12. And we want to express this thing in equivalent form. So we have natural log of x plus 1 equals 2, and then we also have natural log of x minus 1 equals 4. Okay, so to do that, and I think I'll just send this up here to the window. Put it in the corner so we have it. I want you to recall that log base a of x equals y if and only if a to the y equals x. So we can use that fact with this natural log and recall natural log is the same as log with a base of e, where e is that number. So to rewrite natural log of x plus 1 equals 2, the first thing we want to do is say log base e of x plus 1 equals 2. And if you remember, the way we wanted to organize that is we say log base a of x equals y if and only if a to the y equals x. In doing so, we can match terms. We see that e and a match, so wherever I see an a, I put an e. The y term matches with 2, so wherever I see a y, I get 2. And the x term matches with x plus 1. So the answer we're looking for is e squared equals x plus 1. Alright, so let's go on to the next slide. For this one we have the natural log of x minus 1 is equal to 4. So recall that that's the same as log base e of x minus 1 is 4. So if we rewrite that as log base a of log base a of x equals y if and only if a to the y equals x, then by matching terms we see a matches to e, we see y matches to 4, and x matches to x minus 1. So our final answer is e to the 4 equals x minus 1. Now you might ask yourself why we're not solving this, but that's not what we're asking to do. For these problems, we just want to write them in their equivalent form. Later is when we will get around to actually solving them for the unknown variable. Alright, let's do some more problems. So for number 18, we want to write in equivalent form. So we have 2 problems. We have e to the x plus 1 equals 0.5, and we also have e to the 0.5x equals some number t. So to do these, we could say, alright, well, I know e to the x plus 1 equals 0.5. And I know that a to the y equals x if and only if log base a of x equals y. So by matching terms, I see that a matches to e. I see that x matches to 0.5. And I see that y matches to x plus 1. And recall that this is the natural log. So we can write that as natural log 0.5 equals x plus 1. Alright, doing a similar problem, we say e to the 0.5 x equals some t. And then we say, okay, well, a to the y equals x if and only if log base a of x equals y. So we match. We say a matches to e, so log base e. X matches to t, log base e of t. And y matches to 0.5x. So that's a natural log. So our answer is natural log t equals 0.5x. Easy peasy. Okay, so we did some expressions in equivalent form, but now we want to do some evaluations. And the first things we want, the first one we want to evaluate is log base 4 of the square root of 2. Okay, so to do that, we say, okay, well, I somehow have to get this term right here to be in terms of a power of 4. So I can say, well, I know that the square root is the same as saying 1/2 power. And then if I think about it, I can say, well, I know that 2 is the square root of 4. And from there I can say, well, I know that just like before, that the square root is a 1/2 power. And then I can say, well, okay, if I've got a power to a power, so power to a power, I can rewrite that as a multiplication of powers. So log base 4 of 4 to the 1/2 times 1/2, which gets us log base 4 of 4 to the 1/4. Okay, well we have, remember that property 3 says that if the base of the log and the argument match, then the exponent is what sort of pops out. So this gets us a final answer of 1/4. Okay. So we're still working on number 28. There's actually 3 parts to this problem. The next one is log base 4 of 1/2. Now in the next section we'll learn probably an easier way to do this, but as a good mental exercise we can say, alright, let's think about 2, or rather this 1/2, in terms of powers of 4. So the first thing I want to do is write this is 2 to the negative 1. Remember that negative powers give you the reciprocal. So 2 to the negative 1 must be 1/2. Then, like before, we can say, alright, well, I know that 2 is the square root of 4. And then I can say, okay, well, I know that the square root is also can be written as a power of 1/2. And then I get that property that I can multiply my exponents. Then I get log base 4 of 4 equals 1/2. And property 3 tells us then that the final answer must be negative 1/2. All right. Let's do one more. All right, so we're still evaluating. But now we see that we're doing log base 4 of 8. Well, getting this in terms of 4 is not so bad. The first thing I could do is I could just, if I happen to know that directly, I could jump straight there. But it may be unlikely that you know directly how to get there. Well, I could say I know that 8 is the, let's erase that. That looks ugly. I know that 8 is the square root of 64, which allows me to write that as 64 to the 1/2. Now what I also know is that 64 is 4 times 4 times 4. Because remember, 4, well, it's not wanting to work. It's wanting to move it around. There we are. 4 times 4 is 16, and then 16 times 4 would be 64. So writing that as a power, I have 4 to the 3rd to the 1/2 power. And then from there, I could say, well, by the power, or by the laws of exponents, I can write the power to a power as just a multiplication of their powers. So that becomes log 4 of 4 to the 3/2. And now we can apply property 3 yet again to get us a final answer of 3/2. So you see property 3 arising a lot in these types of problems. Alright, well that concludes the evaluation section. Let's do one more graphing. Okay, so this is number 62. And they want us to graph the natural log of the absolute value of x. And list the domain, range, and asymptote. Okay, this one's going to be probably a little tricky if you're not used to dealing with absolute value functions. So let's take a look here. Alright, so I'm going to count these in terms of e's. I'm going to call that e. Let's see, let's erase that. If that's e, then this is going to be e squared. So this is negative e. This is negative e squared. It's going to be 1, and this is going to be 2. Now what we know about the natural log function, or the absolute value function rather, is that it's defined what we call piecewise. And by that I just mean it's defined differently on different pieces. So the absolute value is equal to whatever you put in it, as long as whatever you put in it is not negative, so it's positive or 0. And it's equal to the opposite of whatever you put in it if it's negative, which makes sense, right? We have a negative 2 inside of an absolute value. It pops out as the opposite of that, which is positive 2. So what that tells me is that as long as I don't punch 0 in there, then the absolute value is positive. And if you recall, the domain of the natural log of x without the absolute value is all the positive numbers. So what that tells me is that the domain of the natural log of the absolute value of x is just any number that's not 0. So whether you plug a negative or whether you plug a positive in there, it's going to be okay to plug in. Alright, let's slide this over. Now, since the absolute value of a positive number is still positive, so, absolute value of 2 is 2, absolute value of 10 is 10, etc., then what we're going to see is that the graph is going to look, whoops, this is bad. Let me erase all this here. Okay, it's not letting me erase it. Let me draw over it with some black. It's a pretty cheap way to erase something, but you gotta do what you gotta do. Now it just looks like a regular chalkboard. So we need this points -1 and -1. So recall that, log of any base of 1 is 0. So it's always going to go through here. And then it's going to go through the point 1e. And it's going to go through the point 2e squared. But if you think about it, think about it this way. Log, if I plug in a -1 in there, well, that just comes out as a positive 1, which is still 0. And if I plug in, well, log base e, rather, log base e of -e, well, that's log base e of e, which is 1. And so on and so forth. So what we actually get is this kind of graph. So it has that even behavior, which tells me that the range of the function is unaffected. I mean, it's the range actually isn't affected at all, but it's going to have the same range on both sides of the y-axis. And recall that you can never have 0 in the natural log, or any log rather. So our asymptote is the line x equals 0. Alright, well there you have it. That is everything for section 4.3. Keep checking back for more examples, and thank you for watching.